Hey everyone, this is Karthik Chilakapati, and I'm having the experiment creative assignment, and I'm just going to be finding the velocity at the edge of a rolling object. So introduction, the purpose of this is that we're trying to find the velocity at a point of a water bottle that's not at the center, using the translational velocity at the center of mass, the radius, and the angular velocity. So to compare this value to the velocity, and we're also trying to compare this value to the velocity of that point from the tracker. So we're just gonna see what the velocity is in the tracker at that point. Um, so we have our 2-point equation here for just finding velocity at a specific point that's not at the center. So VC minus omega cross RCP. And I just stated that our center of mass velocity is our position of the center of mass dot, and our angular velocity is theta dot. So pre-lab info, what I did to set up this lab, basically the materials I got, I needed something cylindrical to roll, so I took my water bottle and put the flat base towards the camera. I took a brick and wooden plank to set up our ramp setup, and took a camera to record this motion. That was just my phone, and then I had a tracker app on my laptop, which was used to extract all the data that we need. So procedure, just setting up the ramp with the brick and wooden plank, rolling the water bottle down the ramp, and using the camera to record the motion. Here I just included like a sample of like what we're trying to find. We're trying to find this contact point velocity over here, or basically at the bottom of the ramp. Basically at the bottom of the ramp we have our velocity. So with that data and the angular velocity at the bottom, we're just trying to find the bottom point's velocity. So I also took some measurements. The length of the ramp was 1.2 meters. The bottle radius was 0.0254 meters because it was about like an inch-ish or inch and a half. And the initial velocity was just 0 meters per second because we're letting it go from rest. Here's the video I took of releasing the water bottle. This is in slow motion, so I'm just going to skip through it, but we can see it rolling down. And in this experiment, basically we're trying to find the velocity right over here. So the bottle's at the bottom of the ramp, and we're trying to find like this contact point's velocity. Not real. Oh, realistically, it would be the same for any one of these, but it's basically at the bottom of the ramp. So once I took this video, I put it in a tracker and I set my calibration stick over here for 1.2 meters of the length of the ramp. And then I also set my axes just to make the x-axis along this ramp so it's easier to interpret the graphs. And then I use the auto tracker function to track the center of mass of this bottle as it's going down. As you can see here, this is being recorded over here. And then I got some data. I got the time, the x position, y position, velocity, and the angular velocity, which is in degrees per second, so I had to convert it in an Excel spreadsheet afterward. But this velocity is our center of mass velocity. So finding velocity using this equation, basically I went towards the end of the data over here. Basically I went all the way to the bottom and took the velocities at the bottom, averaged them a little bit to get a good estimated value of what the velocity was at the end of the ramp. Did the same thing with the angular velocity, except I converted it to radians per second first because they gave it to me in degrees, and I multiplied that by the radius of the water bottle, and then it turned out that VP at the bottom using the equations was about 2.5 meters per second. But then I tracked it again with the angular velocity using the tracker itself, where instead of tracking the center of mass, I basically tracked the point on the whole circular part. Like I basically followed the circle as it was moving. And using that and doing data reduction, I got that it was 3.54-ish meters per second squared. And I found out the percent difference from this to see how different these two values are, and it turned out that it was about 41.8%. Before we get to this, so some errors that could have happened in this experiment were that the way the video was taken, it could have been that the calibration stick will not have given justice to the exact measurements because it basically looked like the face of the water bottle wasn't always parallel to the camera, so the angular parts of it could cause the auto tracker to miscalculate where the center of mass of the water bottle is. And I also think the tracker itself to track the oh, sorry, that should not say angular velocity. That should say no, that should just be normal velocity. But um just for finding normal velocity, also tracking that would also be hard because it also was not a clear full 2D video where the face of the bottle was like in the same position the whole time. Also, that should just that there should be no angular there. This is just normal velocity. But how this relates to aerospace engineering, basically many components of planes involve rotation and velocity. For example, little even tires on a runway. Knowing the velocity at certain points of a tire can possibly help solve issues that could rise in landing and takeoff. And uh, this also can involve pitch, yaw, and roll because we're also dealing with angular velocity here. So that's also an important factor when um, looking at airplanes because right now we only calculated the velocity at like the bottom of a wheel, but it could be like at the edge of a wing or any specific part of the aircraft. So knowing these concepts can really help understand how aviation occurs. And that is it. Thank you.